All right, get ready. Because today, we are really going to get our hands dirty digging into this R3GN paper.
Definitely exciting stuff.
It's a new development in these GANs, generative adversarial networks.
Yeah.
And we've talked about GANs on the show before.
We have. They're really interesting. I mean, they've been around for a little while, but they've always had these problems.
Yeah, and that's, I think, why this is so exciting, because they are so powerful.
Yeah.
The idea of having these two neural networks, one generating content and the other judging it.
Mm-hmm.
It's like that classic artist and critic dynamic, right? But they're so hard to train. So R3GN is coming in and saying, hey, we've found some ways to make this a lot more stable.
Yeah, and a lot faster. I mean, one of the things that I found really interesting about this paper was the fact that they can generate high-quality images in just one network evaluation.
Oh, wow.
As opposed to diffusion models, which, kind of the hot new thing, which need many.
So they're saying it's much more efficient.
Much more efficient.
And just as good or better.
Yeah. I mean, that's really the thing that is so intriguing about this paper, is that it's not like some, brand new algorithm or anything like that. It's really a very clever combination of a lot of existing techniques that are carefully kind of selected and applied in a way that addresses some of the inherent weaknesses of these traditional GANs.
And what are those weaknesses? I know one of them is like mode collapse or mode dropping, where, the generator gets stuck, and it just produces the same kind of limited content over and over again.
Exactly.
Like you've got this, artist, and they can only paint landscapes.
Right.
You ask them for a portrait, and they're like, no, I just do mountains.
Yeah, that's exactly right. And the reason for that is because of the way that the traditional GANs are trained.
Right.
You've got this generator and discriminator, and they're essentially playing this like zero-sum game.
Yeah.
Each one trying to kind of outsmart the other. And it can lead to a very narrow focus, where the generator finds one trick that fools the discriminator, and then it just kind of keeps doing that same trick over and over again.
Right. So it's like, okay, I found the way to trick you. I'm just going to keep doing that same thing.
Yep.
So how does R3GN help? How does it help kind of open up the generator to be a more well-rounded artist?
Well, it starts by changing the rules of the game a little bit.
Okay.
So R3GN is building on this idea of what are called relativistic pairing GANs, or RPGNs for short.
Okay.
And what's different about these is that instead of the discriminator looking at the generated image in isolation and saying, okay, is this real or fake?
Yeah.
What it does is it compares it directly to a real image.
Interesting.
So now the generator isn't just trying to be real, it's trying to be more real than a real image.
Oh.
So there's this kind of competition going on.
I like that.
Right. Which forces it to kind of constantly improve and create more diverse outputs.
So it's like, all right, let me try to one-up you.
Exactly.
I see what you did there, but I can do it better.
Yeah. But here's the catch. These unregularized RPGNs, they sound great in theory.
Okay.
Often they struggle to converge in practice.
Okay.
And you can kind of think of it like, a car that's spinning its wheels in the mud. There's lots of effort, lots of energy being expended, but it's not actually making any progress.
That's not going anywhere.
And the authors actually show this mathematically, that with certain types of data distributions, the training can actually become unstable.
I got it.
And so this is where R1 and R2 gradient penalties come in.
Ooh, now we're getting into the nitty-gritty. So break those down for me.
Okay, so imagine you're teaching a dog to fetch, right?
Okay.
You want it to bring the ball back to you. You don't want it to run off with the ball.
Right.
So what you do is you use positive reinforcement, treats, praise, to kind of guide its behavior.
Yeah.
That's kind of what gradient penalties are doing.
Okay.
They're adding this little nudge to the loss function that encourages the discriminator to behave in a way that leads to more stable training.
So it's like every time it makes a good judgment, you give it a little treat. It's like, okay, I'm going to keep doing that.
Exactly.
Yeah.
And so R1 and R2 are two specific types of gradient penalties.
Okay.
R1 penalizes the discriminator when it's too harsh on real data.
Okay.
R2 penalizes it when it's too lenient on fake data.
Interesting. So it's like we want you to be in the sweet spot. We don't want you to be too extreme in either direction.
That's a great way to put it, yeah.
So why both? Why not just one?
Well, that's a great question. And that's one of the things that I think is really insightful about this paper.
Okay.
They show that using R1 alone can actually still lead to instability, especially with these really complex data sets.
Oh, interesting.
And so it's only when you combine both R1 and R2 that you create this kind of sweet spot, this equilibrium, where the generator and discriminator can really learn from each other effectively without spiraling out of control.
And they tested this on a particular data set.
They did. They used a data set called Stacked MNIST.
Okay.
Which is specifically designed to be really challenging.
Got it.
In terms of mode coverage. And the results were really clear. R1 plus R2 equals stability. Anything less, and you risk divergence.
Got it. So we've got this kind of loss function under control now.
Yep.
But R3GAN doesn't stop there. Right. They're also looking at the architecture.
They are, yeah. And this is where things start to get really interesting, I think.
Okay.
Because traditional GANs, they rely on these kind of outdated architectures, like the ones that you see in StyleGAN.
Okay.
R3GAN just throws that out the window and says, no, we're going to use modern architectures like ResNet.
ResNet, oh yeah.
The one with the skip connections?
That's right. And ResNet has been making it's made huge improvements in all kinds of areas of deep learning.
It has, and for good reason.
Yeah.
The architecture of ResNet is just much more efficient. It allows for smoother information flow within the model. It's like upgrading from a, clunky old computer to a sleek, modern machine.
Oh, I like that analogy.
But that's not the only architectural trick up their sleeve. They also do this really interesting thing where they ditch normalization layers.
Okay.
Now, normalization layers are, pretty common in deep learning models.
Yeah, you see them all over the place.
You do. They help to kind of keep things running smoothly during training. But the R3GN authors argue that they actually interfere with those gradient penalties that we were talking about.
The treats for the discriminator.
Exactly. And they might even be hindering the performance of GANs in general.
Wow. So they're saying just get rid of them?
Yeah, it's a pretty bold move to just completely ditch something that's so fundamental to a lot of these models.
Yeah, so how do they ensure that the model can still learn effectively without those normalization layers?
Well, they've got a few other tricks up their sleeve. One of them is called fix-up initialization.
Fix-up initialization.
Yeah, and it's a way of setting the initial weights of the model.
Okay.
So that it starts off in a good place, even without those normalization layers to kind of guide it.
I see.
It's like giving the model a solid foundation to build upon.
Got it. So instead of having the guardrails there, they're just like, no, we're going to start you off in a good spot and you should be good.
Exactly.
Okay. So we've got the stable loss function, we've got this new modern architecture, and then a few other little tweaks to make sure everything is running smoothly.
Right.
But how does it actually perform?
That's the real question, right?
Yeah. Does it live up to the hype?
Well, the results are pretty impressive.
Okay.
They tested R3GN on a variety of different data sets, including some really popular ones like CIFAR 10, FFHQ, and even ImageNet.
Wow, ImageNet. That's the big leagues.
It is. And you know what?
What?
R3GN went toe-to-toe with some of the best generative models out there, including diffusion models.
No kidding.
Yeah, they really put it through its paces.
So give us the details. How did it stack up against the competition?
Well, one of the key metrics they looked at is the FID score.
Okay, FID score.
Which basically measures how similar the generated images are to real images.
Got it.
And across all these different data sets, R3GN consistently achieved FID scores that were either on par with or even better than the competition.
Wow. So it's right up there with the best of them.
It is, but there's another key advantage that I think really makes R3GAN stand out.
Okay, what's that?
And that's its efficiency.
Right. You mentioned before it can generate an image in just one network evaluation.
Exactly. Whereas those diffusion models often need multiple rounds to get a good result.
So that's a big deal, especially for applications where speed is critical.
Huge.
Yeah, like real-time stuff.
Exactly. Imagine you're working on a real-time application, maybe something like generating personalized avatars or creating special effects on the fly.
Right.
With R3GN, you can get those high-quality results without any lag or delay.
So you're not waiting around.
Nope. Instant gratification.
Now, I do remember hearing that some GANs have been kind of accused of cheating a little bit.
Oh, yeah.
By using pre-trained ImageNet classifiers.
Right. It's like they're getting a sneak peek at the answers beforehand.
Exactly.
Yeah.
So did R3GN resort to any of these tricks?
No, they played fair.
Okay, good.
They achieved these impressive scores without relying on any pre-trained ImageNet classifiers.
So it's legit.
Totally legit. And remember that issue of mode collapse we talked about earlier?
The artist who can only paint mountains.
Exactly. Well, they specifically tested R3GN on that really challenging stacked MNIST dataset with 1,000 modes.
1,000 modes. That's like asking the artist to master every single style imaginable.
It is a real test of versatility.
So how did it do?
Passed with flying colors.
Wow.
R3GN successfully generated diverse samples from all 1,000 modes, showing that it can truly cover a wide range of that data distribution.
That's incredible. So it's stable, efficient, fair, and it can handle a huge variety of different modes.
Yep. It really is pushing the boundaries of what GANs can do.
It sounds like it. So where do we go from here? What are the next steps for R3GN and for GAN research in general?
Well, the authors of the paper, they seem pretty excited about exploring different normalization techniques. They completely ditched normalization layers in this version of R3GN, but they are curious if there might be some other ways to do normalization that could lead to even better performance.
Without sacrificing stability.
Right. It's always that balance, right? You want to push the boundaries, but you don't want to break things. And of course, they want to see how R3GN performs on even larger, more complex data sets.
Yeah.
It's like taking an athlete who's dominated local competitions and seeing if they can, compete on the world stage.
Yeah.
Can they handle the big leagues?
Right. And speaking of pushing boundaries, I was thinking about combining R3GN with other cutting-edge techniques.
Yeah.
Like attention mechanisms, like transformers.
Right.
That have been revolutionizing, natural language processing.
Yeah.
I mean, could we see some kind of a fusion of R3GN and transformers in the future?
Oh, that's a really interesting question. I think that's definitely an area that's ripe for exploration.
Yeah.
Because combining the stability of R3GN with the power and flexibility of transformers, that could lead to some really groundbreaking results. Imagine the possibilities for image generation, video synthesis, even 3D modeling.
Yeah, it's pretty amazing.
It's pretty mind-blowing to think about all the potential applications. But of course, with great power comes great responsibility. As these AI models become more and more sophisticated and they're capable of generating this hyper-realistic content, I think we really need to be mindful of the ethical implications.
Absolutely.
Yeah.
How do we prevent misuse?
Yeah.
How do we ensure transparency and accountability? These are really important questions that I think society as a whole needs to be thinking about.
Right. It's not just about the tech itself. It's about how we use it, how it shapes our world.
Exactly.
And how we can make sure that it actually benefits humanity.
Well said. Well, I think this is a good point to sort of wrap up our deep dive, and just recap what we've learned about this really game-changing approach.
Yeah.
R3GN.
So I think first and foremost, R3GN really shows us that achieving stability and high performance in GANs, it doesn't always require inventing something totally new.
Right.
It's often about understanding the fundamentals, identifying the weaknesses, and then finding creative ways to address them using the tools and techniques that we already have.
It's like clever engineering.
It is.
Yeah.
It's about a deep understanding of the principles at play.
I like that.
And by combining those really solid mathematical principles with these modern architectures like ResNet, R3GN achieves this level of efficiency that I think really sets it apart, especially when you compare it to these computationally intensive diffusion models.
Yeah.
Generating high-quality images in a single network evaluation, that's a game changer for real-time applications.
Absolutely. So as we wrap up this deep dive, what's the one big takeaway you want our listeners to walk away with?
I think it's this. R3GN is a really powerful example of how less can be more. It's about simplicity, elegance, and a deep understanding of the underlying principles. By focusing on stability, efficiency, and fairness, R3GN has not only pushed the boundaries of what GANs can do, but it's also opened up this whole new world of possibilities for how these models can be used in the future.
And on that note, we leave you with a final thought to ponder. This is just the beginning for R3GN. What happens when we combine it with even more advanced techniques, like those transformers that we were talking about? What will the future of GANs hold? How will they shape the world of image generation and beyond? That's something for you to explore and contemplate. Thanks for joining us on this deep dive.